good afternoon to everyone. Thank you for joining us today. In this session, we'll be discussing dust collection system design with a focus on fans. My name is John Daniel. I lead our corporate efforts here to support engineering firms at Donaldson Company. We also have Amy Miller on with us today. She's our training manager. She'll be working behind the scenes and we'll be moderating the Q&A session at the end. Today's webinar will focus on proper fan design for a dust collection system. We're going to start off today's webinar talking about the basics of dust collection, including the fundamentals that pertain to fan design. We'll get into the different types of fans, fan arrangements, fan controls, how fan curves can properly size a fan for optimal performance, and good examples of both good and bad design. We'll finish up with everyone's favorite part at the end, the Q&A session. Here at Donaldson Company, we've been solving customers' complex filtration challenges for over 100 years. We were founded in 1915 by Frank Donaldson Sr., who invented the world's first filter for a tractor engine. Today, we're one of the largest providers of unique filtration technologies. We excel at producing high-quality filters and equipment. We pride ourselves on having a local reach and a global touch, And our world headquarters is here in Bloomington, Minnesota. We have about 54 manufacturing plants and 23 distribution centers around the world. As you think of questions throughout the webinar today, please feel free to type them into the chat box, and Doug will answer them towards the end of our session. And during the webinar, Doug may ask you a few questions. You can respond with a reaction emoji. You can access these by clicking the face icon at the bottom of your screen. And with that, I'm pleased to introduce our featured speaker today, Doug Strausser. He's a territory manager for Donaldson out of our Minneapolis office, working for Pearson Arnold Technologies. He's been in the dust collection industry for over 27 years and has a bachelor's degree in industrial engineering from the University of Minnesota. I also need to mention that here at Donaldson, we call him Doug the Fan Guy because you'd be hard pressed to find anybody else who knows more about industrial fans for dust collection systems than him. And with that, I'm going to turn it over to Doug.
Well, good morning, everyone, and thanks for joining us. Good morning, John. Good morning, Amy. I guess before we get started, we'd like to ask you about your experience with sizing and selecting fans. If you would please select the reaction emoji on the screen that best aligns with your experience level.
All right, looks like we have quite a few people with some experience and a little experience. So you've got pretty good group here of people that understand what they're talking about, looking to learn more.
Well, fantastic. Great. It's really helpful for us to know the experience level as we get started with this. So we're going to do kind of a general overview. And as you do have questions, please log them into the chat and we can talk about those after the end of the program. But we'll try and cover things that might be of interest to all experience levels. So let's get started. So we'll start with the basics for those of you who might be new to dust collection system design. There's, of course, a lot of important reasons to control dust, fume, and mist. These include safety concerns and hazards, improving air quality for the employees, exposure control, reducing potential dust in the breathing zones of the workers operating the processes. There's environmental concerns, the EPA standards for exhausted environmental air quality and outlet emissions requirements. And of course, cleanliness, concern about the overall cleanliness of the facility. Well, here's an animation of a typical dust collection system. A blower or fan creates an airflow, which is used to capture dirty air with a hood, and then convey the material through a series of ducts to a dust collector. Here, the contaminant is separated out and clean air passes through the filter media to the fan, where it's discharged to atmosphere or maybe even back to the facility. If one component in a dust collection system, such as the fan, is poorly designed, the whole system is affected. When we design a system, there's a lot of factors that are considered. You can see some of them listed here, like the material being collected, the static pressure losses, future expansion, probably more than most people realize. The publication shown here is the Industrial Ventilation Guide, written by the ACGIH, which is a nonprofit scientific organization that advances occupational and environmental health. The guidelines in it are considered by most in the industry, including OSHA, as the standard for proper ventilation design. The ACGIH offers multiple courses throughout the year on system design using this Vent Guide as a textbook. I've been to multiple courses myself over the years, and if you want to get more into system design, I recommend you check it out. They're great courses. There's a lot of different formulas that we use in system design, the most basic and widely applied being airflow. The formula is Q equals V times A. The Q is the volume of air flowing through the system, often referred to as CFM, or cubic feet per minute. To get the airflow, we multiply the velocity of air, which is the measure of linear speed for an object, by the area of the hood or duct that the air is flowing through. This formula is one of the basic building blocks of dust collection system design. We start at the pickup points and calculate using this formula to get the needed airflow of each pickup. This will then give us the total CFM needed for the system. This formula is also used when calculating the needed velocity within the ductwork and allows us to size the fan properly. Throughout the system design, we refer to Q equals VA over and over. These four terminologies are important when it comes to fan design. Differential pressure drop, or delta P, that's the condition of the filters in the dust collector, the difference in static pressure between the clean and dirty side of the filter. We measure this in inches of water gauge. The static pressure is the resistance the airflow must overcome due to the system components, the resistance of the duct from between the pickup point and the dust collector. This is also expressed in inches of water gauge. The brake horsepower, BHP, that's the power required to be provided by the fan motor. And then decibels, dBA, the unit of measurement for the sound level. When I'm designing a system, the very last thing I do after completing all the airflow calculations is to select and size the fan. The fan is an important component of the ventilation system as it supplies both the energy to move the air through the system, or the velocity pressure, and the energy to overcome resistance to flow, or the static pressure. It has two job responsibilities. First, a fan must deliver the necessary volumetric flow at the needed static pressure to drive operation of the system. Since collectors can operate with clean or dirty filters, the required airflow must be maintained over a range of static pressures. Secondly, the fan you select should be able to deliver the desired static and airflow with an appropriate energy efficiency at an acceptable sound level. Those are the challenges. When it comes to fan design, we're looking at the total system static pressure. This is the sum total of all the component losses in the system. Those of you who attended the last webinar on duct design with my coworker John Schmidt just a few weeks ago talked about this quite a bit. Some examples of components that will create resistance in the dust collection system include the hoods, the pickup hoods, the ducts, those straight runs, elbows, and branch entries, the collector and filters, and then any ancillary components that might be in the system, such as a fan silencer, spark cooler, diverter valves, rain hoods. All of these add resistance to airflow and play an important role in fan selection. So let's do an example. Let's say the hoods in the system totaled 2.5 inches water gauge. The ductwork, including the straight run of duct, elbows, and branch entries, totaled 5.5 inches. In terms of the filters, new unseasoned filters will be in the range of 1/2 inch to 2 inches water gauge, and then they'll be in the range of 2 to 4 inches during the greater portion of their life due to the dust cake on the filters. And then towards the end of their useful life, they might be in 4 to 6 inches of water gauge and might not be able to be pulsed down anymore. So I typically include about 6 inches water gauge to account for these dirty filters. The filter to the fan ducting in this example is 1 inch of water gauge. And then let's say we have a spark cooler in the system. This might be a welding application or a laser table or something like that. That spark cooler is going to add another inch. So the total system static pressure for this example is 16 inches water gauge. Fans are sized using fan curves, which is basically a graphical representation of a fan's performance. The fan manufacturers perform actual tests to find out the static pressure value for the fan for different airflow rates to plot this fan curve. Well, let's say I needed to select and size a fan for that 16-inch water gauge example that can handle 3,000 CFM for a laser table application using a cartridge collector. I inputted the information into New York Blower's fan selection system since they're our preferred vendor for custom fans. And this is the fan curve for one of the options that it gave me. Let's talk about how to read it. On the left axis, or the left-hand vertical side of the graph, we have static pressure. On the x-axis, or the bottom, we have airflow. And on the right axis, we have brake horsepower. The green line represents the static pressure curve, which tells us the relationship between the static pressure capabilities of the fan compared to the fan's airflow at a given fan speed. In other words, it shows the fan's performance. If you follow it from left to right, it starts at about 25 inches, goes up slightly and peaks around 28 inches, and then steadily goes down as the airflow increases. The gray line is the system curve. Where the fan line and the system line intersect is called the operating point, or the point where 3,000 CFM and 16 inches of static pressure intersect. The purple line is for horsepower, which tells you how much horsepower it takes to move that air. So we look at the operating point, follow it to the right, and we know it'll take about 14 horsepower to move 3,000 CFM at 16 inches water gauge. I'll give you some examples of fan curves for different scenarios later, but I wanted to make sure everyone understood how to read one. Let's talk about different types of fans. The most widely used types of fans in dust collection systems are centrifugal fans. A centrifugal fan consists of a wheel or impeller mounted on a shaft. It's normally rotating in a scroll-shaped housing. The air enters the wheel axially and exits at a 90-degree angle. The most common centrifugal fan designs are backwardly inclined and radial blades. Here's the backward inclined fan, or an example of one. This is Donaldson's TBI fan, or turret backward inclined. The backward inclined blade, or the TBI fan in particular, has solid flat blades. It's capable of handling a little bit of dust or a little bit of moisture. We get medium to high amounts of airflow out of a backward inclined. It's not for heavier materials, and it's pretty efficient. Now here's an example of a larger fan, probably ground-mounted fan. This exploded view gives us a good picture of all the different components. So let me run through them left to right. On the far left, we've got an inlet flex connection, then an inlet flange. That next piece there is the inlet cone that'll efficiently direct the air into the fan wheel, which is the next component. Then we have the fan housing. Off to the right, the shaft and bearings, motor, belt drive. There's a shaft and bearing guard flying up there in the air. And then behind that fan housing is a representation for a clean-out door, a removable clean-out door that gives you access to the fan blade. The two most common backward inclined wheel types used in dust collection are the airfoil and the single thickness blade. That TBI fan is a single thickness blade. While it's slightly less efficient, that single thickness blade can be used with dry or moist airstreams. The airfoil is a more delicate blade. It's usually pretty thin and it's hollow, and it's most efficient, but really can only be specified for clean, dry airstreams. So here's a typical curve for a backwardly inclined fan. A couple of things that we need to point out here. First, you notice that brake horsepower curve, the green line, that has a peak. In other words, no matter where the fan is operating on that red system curve, it'll never use any more horsepower than the peak of that curve. So that helps us not only with troubleshooting, but also motor selections, just to make sure we never overamp that motor. Another thing I need to point out on the static pressure curve is, where do you select the fan on that curve? Well, as you approach the peak, moving up and down the curve, kind of from right to left, as you approach that peak of the curve, that's where the fan is most efficient. However, we want to select a fan that's not too close to the peak of that curve, because once you get up and beyond left of peak, the fan becomes very unstable. You'll hear surging, you'll feel vibration, there's a lot of turbulence in the fan. And what's happening is the fan is trying to operate at two different flows with one static pressure. It literally doesn't know what to do and surges. It can damage the fan, it can damage the bearings. So we want to make sure that the system is designed with a fan selected not too close to the peak of the curve. So here's one of my favorite pictures. This is just a textbook fan installation. This is a direct drive fan mounted to a nice concrete slab. It has inlet and outlet flex connections and is really just a great picture of what we want to do in the field. So the other type of centrifugal fan that we'll talk about is the radial blade. It's quite a bit different from the backwardly inclined. You can see in this photo here, the blades of a radial blade fan project radially from the hub. These are great for material handling, and that's what they're designed for. The backwardly inclined, we really don't want to have any material in that airstream, but the radial blade can move material. You can tell just by the way it's designed that as that fan's rotating, it's going to want to throw off any material that wants to stick to it. So they're pretty much self-cleaning. They're not as efficient as the backward inclined. We lose quite a bit of efficiency, and that makes them louder. The sound level is going to be higher as well. And this paddle wheel design, as we'll call it, is probably the most common configuration, although there's a huge variety of both radial and backwardly inclined fan designs. As an example, these can be manufactured in various configurations. This one was destined for a recycling plant. And you can tell by the beefy construction, this one was ready to handle just about anything that's going to go through it. And that included beer cans, beer bottles, maybe some soda bottles too, who knows. But these can be built very, very rugged to handle all kinds of applications. So here's Donaldson's radial blade fan. This is the counterpart to the Donaldson TBI fan. This is the Donaldson TRB fan, turret radial blade. Again, it's a material handling fan. This little TRB could be mounted right to the side of a collector. The photo to the right there is an example of a larger ground-mounted radial blade fan. And as you can see, or maybe it's not completely obvious, but in this case, we're blowing from the fan into the Donaldson RF collector. So the material is coming from the inside of the plant into the inlet of the fan and then being blown into the dust collector. Now here's an example of the radial blade fan curve. And you might notice this one's quite a bit different from the backward incline. The first thing that probably stands out is that brake horsepower curve. If you look at that curve, you realize the more air we feed a radial blade fan, the more power it's going to consume. So we have to be careful with selecting the motor for a radial blade fan to make sure there's enough capacity in that motor, enough horsepower capacity to cover maybe an upset condition in the system where it's flowing more air than designed, but the motor can still handle it without overamping. You might also notice that static pressure curve doesn't have that peak like we had with the backwardly inclined. The static or the radial blade fan is happy to run completely closed off to wide open. It's a feature of the radial blades. So fan drives, how are we going to move these fans? Well, they can either be direct drive or belt drive. With direct drive fans, the fan shaft is mounted directly to the motor or coupled directly to the motor. These can be either ground or collector mounted. Those collector mounted fans are great when capacity will allow for them, because as you can see in this photo, it makes for a nice compact installation. We don't have to use up too much real estate for the whole system. Some other common direct drive arrangements, these are the ground-mounted design fans. On the left there is what we call arrangement 8. And in this case, you might notice that the motor is far away from the fan housing, so there's a shaft and bearings in there. So the weight of the fan wheel is supported by that shaft and bearings. As opposed to arrangement 4, the photo on the right, the fan wheel is mounted directly to the motor shaft. So that motor shaft and bearings is carrying the overhung load of the wheel. So these are typically smaller direct drive fans that we would use arrangement 4. The arrangement 8 can be very, very large. And here again are those collector mounted fans. We'll designate these as arrangement 4H there on the left, the H standing for the horizontal shaft of the motor. As you can see, the fan mounted to the side of the collector with a horizontal motor shaft, as opposed to the one on the right, the 4V, and you guessed it, the V is for vertical, with the vertical motor shaft. So belt drive fans, as these fans get bigger, we might want to consider a belt drive fan for a number of reasons. Belt drives offer some advantages. We can adjust the fan speed with a change to the belts and shivs. They might be quieter, less vibration is transmitted from the motor or from the fan to the motor. These are typically larger fans located outside. Another example of where we might want to use a belt drive is when the temperature of the airstream is too much for a direct coupled motor. So we remove the motor, get the motor away from the airstream, and use a belt drive to drive the fan. Some common belt drive arrangements on the left there is what we call arrangement 1. And you might notice that this is a larger motor mounted to a unitary base. The fan and all its accessories would also be mounted to this unitary base. If the motor size allows, we can use arrangement 9, which is the photo on the right, where the motor is actually mounted to the fan pedestal. Another thing I'll point out in this photo is on the inlet side of the fan, you see what's called the inlet box. This has some distinct advantages that we'll talk about in just a second. Here's another great photo, another textbook installation. This is a pretty sizable fan, but again, the takeaway here, fan mounting, putting this on a concrete slab is the preferred method. That gives us a great inertia base and provides a fantastic foundation for a big fan like this. Now here's that unitary base again, and like I mentioned, the unitary base is going to be used in a couple of situations. Primarily when we've got multiple components, like here again is an inlet box on the inlet side of the fan. We can mount the inlet box, the drive, be it arrangement 8 in this case, or a belt drive fan. All the components can be mounted on a single unitary base that eases installation. The other time we might want to use a unitary base is when we're doing isolation. The photo on the right there shows the fan on a unitary base with spring isolation underneath. When we're putting one of these systems up on a mezzanine or on a structure of some type, we always want to use spring isolation. And that protects the fan from vibration from other equipment coming to the fan, or from the fan itself sending vibrations out into the plant and affecting other equipment. This is an example of what we call an inertia base. This is that unitary base, but when the fan is installed, we'll fill this base with concrete and give it that heavy mass, just as if it was bolted to a concrete slab. We can also put these inertia bases on spring isolation. So we could do this up on a structure, fill it with concrete, and use spring isolation to avoid transmitting vibration through a structure. Let's talk a little bit about fan controls. Because of the static pressure changes in a system due to the filters as they age, as the dust builds up on the filters and the pressure drop comes up, it's important to consider what type of fan controls you're going to use or specify for a dust collection project. We can control fans electronically or by manual configurations. A Donaldson airflow controller with a variable frequency drive, or VFD, automatically manages the fan motor speed, so the fan is used only as much or as little as needed for optimum performance. For example, when the filters are getting towards the end of their useful life, when we're up to that 6 inches of water gauge or so, the VFD speeds up the fan to overcome the additional static pressure. So the system is still performing at design airflow. Customers that use VFDs appreciate the energy savings, longer filter life, and optimal collector performance. We used to specify VFDs really only for larger systems when this type of technology was new to the market. But as design has evolved and costs have come down, we're now seeing them specified on even small systems. If the budget allows, the VFD, or variable speed control electronically, is the way to go, hands down. If you spec a system without a VFD, the fan should have at least a mechanical damper so the operator can manually control airflow. They generally have a lever that the operator moves to open and close the damper as needed. For example, immediately following a filter changeout, when the pressure drop is low and the flow is high, the damper should be closed to a point that it maintains proper airflow. Since clean filters have much lower static pressure, the airflow will be too high if we leave the damper fully open. Throughout the life of the filters, the operator should adjust the damper as needed until it's fully open to maintain the design airflow. Fan dampers can either be on the inlet or the outlet. Here's a couple examples of outlet dampers. The parallel blade outlet damper on the left is the lower cost of the two, but is fairly limited in performance, as the control arm movement is not proportional to the degree of control. It takes a pretty good arm sweep to adjust the parallel blade damper. So only specify this type when a small degree of control is required or when full open or full closed operation is needed, such as cold starts. An opposed blade outlet damper, the one on the right there, is a bit more expensive because the blades move in opposite directions. It's got some linkage in there that costs a little bit more, but it allows for more control. Specify this type if the customer needs a broader range of control or more even airflow distribution exiting the damper. This is an example of a fan inlet damper. You notice the damper in the inlet of the fan. This is a damper option to consider if you're specifying a backwardly inclined fan without a VFD. It pre-spins the air prior to the fan wheel. However, the pre-spinning rotation will change the fan curve and reduce both the fan capacity and horsepower. It actually behaves somewhat like a VFD. That pre-spinning of the air doesn't allow the fan wheel to take as big a bite out of the air, and the fan curve changes, very similar to what it would do with a reduction in motor speed. Well, another thing we need to consider in fan systems are the inlet and outlet configurations. On the inlet side of the fan, we need to look at keeping the airflow as linear as possible so that fan wheel can take as big a bite out of the incoming airstream as possible. The example on the left there has a nice long run of straight duct right into the inlet of the fan. This is what we want to see. As long, there's rules of thumb, 6, 8, 10, 12 duct diameters of straight duct in front of the fan. The more the better is what we really want to see. The one on the right there, here we got a giant fan with a large dust collection system. It's a little bit compromised that we've got a shorter run of straight duct into the fan, but real estate's expensive and do the best we can. Well, this is where that inlet box that I mentioned before comes into play. You'll notice on that photo on the left, there's that inlet box. And inside this inlet box, at least on larger inlet boxes, are engineered turning vanes to help direct the airflow and keep it linear as it enters the inlet of the fan. The two pictures on the right are examples of the Donaldson RF dust collector. And you can see using that inlet box how tight the fan can be installed next to the dust collector. Again, real estate is expensive, and anything we can do to make the dust collection system more compact helps. These inlet boxes are extremely handy for this situation. On the discharge side of the fan, we have similar considerations. Again, we want to control that airflow and keep it as linear as possible all the way out the rest of the duct work or whatever duct system might be on the discharge side of the fan. On the left side there, doesn't get much better than that. The fan is actually going through a fan silencer. That's that gray box sitting on top of the fan, and then into a nice straight duct for the fan exhaust. The photos on the right, probably not the greatest configuration. That photo with the question mark on the discharge, not really sure what's going on there or how that came about, but I'm told the plant owner's car was parked next to the building and the fan discharge was pointing right at it. Maybe the dust collector was leaking, who knows? But they needed somebody to fix this, and that was their solution. Not the best, could have done better. That photo on the right there is what used to be considered standard procedure for a rain cap. Much more efficient designs these days. We want to use what's called a no-loss stack instead of that rain hat, which is extremely inefficient. Another thing to point out here, look at that inlet. We've got a 90-degree elbow right in front of the fan inlet. There's just no way that we're going to get good linear flow to get that wheel to be able to take a nice bite out of the airstream. Going to have some losses because of that. But we should really talk about sound levels. Sound is an important consideration that not everybody thinks about when a system's being designed. Fans for dust collection systems can get pretty loud. And one of the reasons for that is the sound frequencies of fans are very similar to normal conversation. So even a fan that's well under an OSHA sound maximum sounds loud because you wind up yelling at each other to overcome the sound of the fan. OSHA's permissible exposure limit for sound is 90 decibels as a time-weighted average of an 8-hour workday. This is why many manufacturing facilities have programs in place to protect workers' hearing, and why I take sound in consideration when making a fan selection. Decibel levels are logarithmic, which means that the decibel level of normal conversation at home is only about 1/4 as loud as the vacuum cleaner. And a chainsaw is about 32 times as loud as the vacuum, which for most humans is considered painful. If I'm deciding between a few different fan options, sound is definitely something I take a look at. The quieter the better, and oftentimes I specify a sound silencer to help reduce it further. But I always try to stay below 85 dBA, which often does require a silencer. Let's talk about fan sizing. Let's do a quick example. We'll start with a small system for the first example. Let's say we're designing a system for 9,000 CFM at 11 inches water gauge. This might be a welding operation with a cartridge collector or something similar. I'm going to go with a machine-mounted direct drive fan. This one in particular is one of those Donaldson TBI backwardly inclined fans. To size the fan, we use the system static pressure of 11 inches water gauge and the airflow of 9,000 CFM, and we line those two factors up. You can see the fan curves on this chart, which tells us the effective range of each fan size. In this case, I selected a TBI 30. You may be tempted to save the customer some money and size it down to a TBI 25, since it falls between the fan curves. When the filters are clean, that TBI would be sufficient. However, it won't provide enough airflow as the filters get dirty. So in this example, I'd go for the TBI 30. For larger systems, we need to do more of a custom fan. Let's do another example and say we have a system in a high altitude location, maybe Denver, Colorado, with an altitude of 5,280 feet above sea level and a higher temperature application such as 120 degrees Fahrenheit. How about 30,000 CFM, 14 inches water gauge, and the customer prefers a manual damper to a VFD. I wanted to show you all the inputs that I use to help determine the best fan for this situation. In this case, I'm using the NearBlower fan selection tool. This is a software program we use to size fans for different applications. This tool is available on NearBlower's website. All the fan manufacturers have some version of a fan selection program that's usually generally available to the public. The first thing I need to do is select the type of fan I want. In this case, I'm going to select two typical backwardly inclined fan categories, class 1, 2, 3, and class 4. If you have no idea what type of fan you might be looking for, you can check all the boxes, but be warned, it's going to slow down the software. So if you do a little research and maybe select just a few different varieties of backwardly inclines and radial blades, it'll speed up the program and work better for you. So next, I'm going to input the fan characteristics or operating conditions that apply to this situation. As you can see on the left-hand side, I inputted the 30,000 CFM and the 14 inches of water gauge. I selected a belt drive since I got a pretty good feeling it's going to be too large to be machine mounted or mounted on the collector. On the right, I inputted the altitude. Now I can calculate the density based on these operating conditions in the outlet damper. And here are my results. More often than not, the highest efficiency selection is going to be the first one in the list there. But there's other things we need to look at. Sound level, horsepower, speed may be a factor. Your customer may have a reduced speed preference. All kinds of different things come into it. You can check each one of these selections and look at all those parameters and make the best selection based on that. So here's what comes up when I select that top of the list there, the highest efficiency one. I can view all kinds of information about this particular fan and verify it's going to meet the needs of the customer. You'll notice where the operating point is on the fan curve. It's not too close to the peak. We've got that 30,000 CFM at 14 inches, drawing 91.2 brake horsepower, and our sound level is about 100 dBA. We're certainly going to need a silencer for this one. Let's say we've got the exact same scenario, and just for example, let's select a radial blade fan. I put in the software program that I wanted a radial blade instead of that backwardly inclined. So here's the radial blade selection, and you'll notice that horsepower jumped up from 94 or whatever it was, up to 132 brake horsepower, and the sound levels up to 109. So the radial blades, like we talked about, are less efficient and noisier. So what not to do? I find that sometimes the best way to show you what to do is by showing you what not to do. I've seen a lot of things over the years, and it's kind of fun to go through this. So let's play a little game. I'll show you a few pictures, and you can chat in what you think is wrong with the fan or the fan design. All right, here's the first one. What do you think's wrong in these pictures?
Okay, we're getting some responses now. Questioning the vibration isolation. So yeah, improper mounting, bad mounting. So looks like most people are turning to the base and the mounting.
Yep, there you go. You guessed it. The one on the left there was a nice try, but we could have poured a little larger slab in this case. You do want to support the entire unitary base or the entire fan base, however it's configured. So that was a swing and a miss. The one on the right there looks like they they got the fan up to the roof and then just decided to keep the 4x4s on it. That's no good. We need a nice inertia base for the fan. And I think someone pointed out that there's no isolators on there either. So this is up on a roof. We're definitely going to want to have spring isolation on that one. Great job. All right, what do you see here? You got to look kind of close to this photo, but hopefully you have some information that was provided that might suggest what went wrong.
Give a moment for people to respond here. Okay, should be dry clean air, worn airfoil, by material wear, abrasive corrosion, water intrusion, erosion. So most people, looks like they're pointing towards abrasion and erosion here.
Yeah, all great answers. This is that airfoil fan blade in a backwardly inclined wheel. And just looking at the abrasion damage to the fan there, the paint coming off, this type of wheel should never be in a material handling application. This may have been just a dust collector that was leaking. I guess we don't know just looking at the photo, but material was definitely going through the fan to the point where it actually wore out the edge of the fan blade. You can see the fan blade there is open. So what happens at this point is material now gets into that fan blade and the wheel goes horribly out of balance. And that can be a dangerous situation if this fan is rotating at a high speed. Excellent. That's exactly what we were looking for. Great job. Okay, these are just kind of fun. What do you see here?
Bad inlets. Yeah, most people are pointing to that inlet. Looks like they listened to you earlier. No straight run of duct on the inlet.
Yeah, I think you're nailing it. That's exactly what's going on. That one on the left, like we mentioned, we want a nice linear full flow inlet to the fan. And this is so compromised. I'm surprised the fan might do 10% of its capacity. The flow is just so restricted with that small inlet and the 90-degree fitting right in front of it. It's just not going to work well. Another thing here I'm noticing is what I call breaking the back of the airflow as it's discharged. The air is kind of following the housing, rotating in a clockwise direction from this angle. And then we're bending it back the other way for no reason that I can decipher. It just creates another loss in the system and wastes power and energy. The one on the right is a little bit harder to see, but it looks like they got this right up to the close to the edge of a roof and made the inlet duct fit. So you've got that super skinny inlet coming in on the vertical, a hard 90 into the inlet of the fan. It's just not going to be able to get full flow and get a good bite out of that airstream. So again, efficiency is horribly compromised. Another thing I'll point out is as much as you want that linear inflow on the inlet side of the fan, we do want the same thing on the discharge. So it's always important to have some length of duct on the discharge of the fan just to help that air stabilize again and get back into a linear flow. That creates the highest efficiency. So this one struck out on both the inlet and the discharge. Great stuff. I think these are my favorites. What do we see happening here?
Okay, we have elbow, issue, outlet design, restricted outlet. Most people pointing to the outlets.
Oh, I saw a lack of belt guard. Hey, that's a great observation. That's very. I've been looking at this. I don't know how many seminars, and I never even considered that. Right on. But the obvious one is, I guess the guy's proud of his work there on the left, but didn't have the material to do a nice transition to the round duct. So we'll just stick the very small round duct right directly to the outlet of the fan. A horrible design. We're going to have significant losses on that one. The one on the right, I'll give them credit. It's probably been running for 184 years. At least it looks that way. But again, we're breaking the back of the airflow, that hard 90 into two small duct, no transition, and no belt guard. Again, great observation. Yep, everybody nailed it. That's exactly what we've got going on here.
All right. Hey, thank you, Doug. Great job. We all know designing dust collection systems can be complicated, and there's a lot that goes into it. That's what we're here for. We've helped design and deliver countless dust collection systems around the world. We have local support in every market, and we're here to help. If you need any support with your project, please feel free to reach out to us. With that, we're going to finish up with some Q&A. Trainers, if you can turn your cameras back on now. Just a heads up that everyone who attended will receive an email that includes your professional development hour credit. There's also a few QR codes on here if you're interested, including our events page for live upcoming webinars. Next month, we'll be discussing electrical controls, and the on-demand page where we post recordings of past webinars. If you have follow-up questions or if you don't get your PDH certificate in your email within a week, my email is on there. You can send me a note. Also, in case you're not aware, we train. We have a 5-hour in-person training class on system design for engineers, which will be held in select cities over the next few months. We just held one in Atlanta, Georgia. The next ones will be in Dallas, Texas on January 28th and Toledo, Ohio on February 4th. We're going to post a link for more information on that, or you can send me an email if you'd like to learn more about that. So we will turn it over to Amy for our first question.
Thank you. Hey, John, would you mind posting that link? I'm not able to do it on my end. If you could post that link for them, that'd be awesome.
Okay.
Thank you. All right. So Doug, first question, this one came to me privately. Can you explain how the no loss stack works?
Yeah, great question. We didn't really touch on that. The no loss stack is a means to prevent rainwater from getting into the fan. So if you remember that slide we had, that picture of the rain cap on top of the discharge duct, we're going to take that off, get rid of that, and set up a no loss stack. And what that involves is a round duct coming off the discharge of the fan, a transition from the rectangular to round, and then a larger diameter round duct surrounding that smaller round duct after the discharge that continues up a little more elevation. What that does, if you think about it, rain never falls straight down. It's always going to fall at an angle. So with that larger duct surrounding the discharge duct of the fan, the rain's going to come down at an angle, hit the sidewall, and drain down that larger diameter duct and exit at the bottom, not even going into the fan. It's such a simple design. It's amazing how well it works.
Thank you, Doug. All right, next question. How much does a fan silencer reduce the sound level?
A silencer is designed specifically for the sound frequencies that the fan produces. And that selection software that we were looking at, that will give you that information. And then adjacent to the fan selection software is a silencer selection program. So the silencer selection program will take all those sound frequencies and their levels and design the silencer to attenuate the sound level to whatever you decide. Now, of course, if you take a 110 decibel fan and try to put a 50 dBA silencer on it, that silencer is going to be the size of a house, just not practical whatsoever. Okay, that's extreme. But there are limits to what can be done efficiently. So the software sizing program will, typically we're looking at a fan that's somewhat over 100 dBA, 110 maybe on the high end. They do get louder, and we do have to deal with that. But we can usually, with a reasonably sized silencer, we can cut 10 dBA pretty efficiently. So again, if you have the chance to go to the fan manufacturers' websites, look for their selection programs and look for their silencer selection programs and play around with them. It's pretty neat what they can offer.
Thank you. Next question. Should we consider vibration monitoring on these industrial fans, especially as our motor horsepowers start to get pretty large?
Absolutely. And that's kind of the key where the cost efficiency comes into play. Larger fans and larger bearing systems get more complicated and of course much more expensive. And monitoring is not that difficult and not terribly expensive. And you can really save some significant downtime by just watching, is the bearing temperature coming up? Is the bearing vibration coming up, indicating that something's wrong, either with, something that happened to the fan, or maybe even just lubrication intervals on the bearings. For larger fans, it's highly recommended, and we'll always include that on a fan quote for a larger fan, at least as an option. Great question.
Thank you, Doug. So the next question came in when you were showing the New York blower tool. So I'm thinking it's regarding that. He's asking, is this program available online? If the person who's asking that, if you meant something else, let me know. But Doug, will you explain to them how to get to the tool, the sizing tool?
Yeah, the one I used in the seminar here is the New York blower sizing tool. That's available on nyb.com, newyorkblower.com, except it's just nyb.com. And I'm trying to think of where it appears I don't know if I know where it appears on the public page. I'm sorry, but
I think it's right at the top. It's kind of the
okay. It should be pretty easy to find.
Yeah.
So I do recommend you play with it. It's very helpful.
Okay. Thank you. All right, let me see. Now I'm going through all of our comments about the stuff that was wrong. All right, so is having the blower before or after the collector more beneficial?
Yeah, that's going to be situation dependent, and I don't mean that to be a cop-out answer, but I would say in a dust collection system, I prefer to have it after the dust collector. And the reason being is that puts everything under a negative pressure. So the whole duct system to the dust collector and the dust collector itself is under a negative. So if there are any compromised ducts or connections, any leakage points, the dust isn't going to be able to blow out because it's under that negative. And for that reason, I really like to put it on the clean side of the dust collector. There's going to be those situations where you have to pressurize the system or blow the material through the system. Dense phase conveying is that way. There might be an addition of a wood hog that's not in the same line as the rest of the dust collection in a large wood facility, and you need to blow that material into the existing collector. It's not as efficient, and you do have the negatives associated with pressure as opposed to vacuum. So I hope that answers your question.
Thank you, Doug. Next question. What codes are applicable to the installation of dust collection systems?
There's a lot of stuff. And I really can't speak to that in a short period of time here. But the one thing I really should bring up is NFPA for combustible dust systems. You need to be well aware of the NFPA regulations that have been adopted by OSHA now for combustible dust systems. And that's a whole nother seminar, and that information is readily available. That's probably the one that comes up in our world most often, is dealing with combustible dust. How does the fan fit into combustible dust situations? In most cases, we need to make sure that the fan is of a non-sparking or spark-resistant design. There's a number of ways we can do that. Of course, the motor we want to consider, is it in an electrically classified area due to a combustible dust, to make sure we select the appropriate motor. That's a big topic, and all kinds of information is available, but it can be challenging to dig through. We're happy to help you with those questions.
Thank you, Doug. All right, so this is a second question from the same person. Are deflector plates required on all dust collectors?
I'm wondering if you're talking about deflector plates in the collector itself to protect the filters.
Maybe?
Maybe,
I'm
yeah.
not sure.
If I'm trying to think of what else that could pertain to. We do have abrasion resistant inlet configurations, ways to protect the filters from abrasive or high density dust. I guess I'm not sure the context of the question, and if you can clarify, I'd be happy to take a shot at it.
Thank you. Yeah, so let us know if you're still on, the person that asked the question. If you have additional clarification you'd like, we'd love to help you. All right, next one. What is the limit of the exhaust stack on the fan before needing a separate support?
Okay, I'm thinking one path, and now I'm wondering if you're just curious about the stack right directly on the discharge. And the first thing I will say about any ductwork, inlet or outlet, on the fan needs to be supported separately from the fan or independently of the fan. The fan housing really isn't designed to take any load. So the question being maybe, how big of a duct can we put on the discharge of the fan? I can't think of any reasons to restrict that other than, there's going to be some resistance the longer the duct is, or any elbows after. But the key takeaway is the weight of any duct on the discharge of the fan needs to be independently supported from the fan itself.
Thank you. All right, next question. We have a radial blower, like a radial blade blower already, but looking to upgrade to a collector from blowing straight into a trailer. Should we upgrade the fan to a TBI?
If the fan you're referring to is taking the discharge of the dust from the dust collector and blowing it into a semi-trailer, that is a very typical radial blade fan application. It can be done with a backwardly inclined fan, but the way you'd want to set it up is you're drawing clean air, maybe outside air or plant air, on the inlet side of the fan, and then blowing into that duct that would convey the air to the trailer. The way I like to do the systems is with a radial blade fan in a closed loop. For example, if it's sawdust, you're going to take the discharge from the collector, run it through the fan, blow it into the semi, and then have a clean air line coming out of the semi-trailer back to the inlet of the fan. So it's a closed loop system. Those work pretty slick. I hope that answers your question.
Thank you, Doug. That was our last question. So we'll give maybe another minute if anyone else is typing something. Not really sure. Just give you
Sure.
another minute. And again, let us know if you have any questions or any follow-up concerns. Our email address is on the screen. John, I changed that on you on the last minute, at the last minute. Sorry about that. So you can go ahead and email it to training@donaldson.com if you'd like. And we'll make sure and answer all your questions for you. So I'm not seeing anything else besides someone saying thanks. You're very welcome. So great job, Doug. Thanks, John. And let us know if you have any additional questions for follow-up, and we hope you have a great rest of your day. Thanks for attending today.